Dr. Rupali Chandar is Associate Chair and Helen Lutke Brooks Endowed Professor of Astronomy in the Department of Physics and Astronomy at the University of Toledo. She received her PhD in astrophysics from Johns Hopkins University in 2000 and went on to postdoctoral positions at the Space Telescope Science Institute and Carnegie Observatories in Pasadena. Her research focuses on understanding how stars and clusters of stars form and change over time in nearby galaxies like our own Milky Way. In other words, she's a big picture researcher. She's been fortunate to work extensively with observations taken with the Hubble Space Telescope. I'm sure you've heard of that. She's a long-standing member of the FANGS research program, and for those of us who are novices, that's physics at high angular resolution in nearby galaxies, which captured the image of a spiral galaxy 32 million light years from Earth using NASA's James Webb Space Telescope. And that image was showcased on a commemorative stamp recently issued by the US government.
Wow.
Rupali was recently one of 2 UT astronomers who will lead fourth cycle observing programs on the James Webb Space Telescope. And these opportunities are highly competitive. Of well over 2,000 fourth cycle proposals reviewed by the James Webb Space Telescope Allocation Committee, only 274 made the cut. And that's only a success rate of 12%. So congratulations. And with the success of her proposal, which is her third successful proposal in 4 cycles on the Webb telescope, she'll be turning the space telescope's lens toward, listen to this, the phantom void in the phantom galaxy. It sounds both fascinating and mysterious. And I have no doubt that she will be a fascinating speaker tonight. As one of her students wrote, she is clearly passionate about teaching and astronomy and wants to help everyone learn and succeed. 100% a great teacher.
Mm-hmm.
Dr. Chandler.
Thank you. That was really such a lovely introduction. All right, so I should share.
That's the right one.
I think that is the right one. Well, thank you guys all for coming out. I know it is cold, it is windy. I let my dogs out right before their border collies and they were not having it. And I was like, oh, I guess I have to go out. So I really appreciate you being here. What I want to do today is keep things very informal. I want to tell you a bit about some of my favorite objects in the universe. I want to tell you a bit about James Webb and how it's been changing our views of many pieces of the universe. Obviously, I'll just walk you through a few of my favorites. And I want to tell you a bit about the role that the University of Toledo is playing with the James Webb Space Telescope in really revolutionizing our understanding of the universe, many, many parts of it. So let me start with just this short video. I wanted to highlight how extraordinary this piece of technology is. And I cannot give it justice, but you can see, let me just play it one more time. This is a very quick version of the James Webb Telescope unfurling. It was launched on Christmas morning in 2021. Did anyone watch? Any of you get up and watch? I made my kids get up and watch. They're older now, so they were like, what? But it was unbelievable. The way that they had to launch it, right, in order to save enough fuel, and for this extraordinary machine, basically, to get from here out to the Lagrange 2 point, which is about 4 times beyond the distance from the Earth to the moon. So it's well beyond that. So it took about a month to get there, and it had to make over, I think, about 100 different maneuvers, including one of the most sensational deployments, which was the deployment of these sun shields. Let's see if we can watch that part of it real quick. So here comes they're gonna get ready to deploy the 5 sun shields right there. There they go. There's 5 of them. They are under extreme tension, and it's this material that is very strong, although I'll tell you a quick story about things always go wrong. The layers are all about as thick as the human hair. And they're these massive 5 independent layers, but they're critically important for this observatory, right? They shield the telescope from the harsh rays of the sun. It has to stay very, very, very cold, just about 40 degrees above absolute zero. And so they're critically important. Well, as they were getting ready to launch James Webb, they were doing final testing on the ground in March 2018. I remember it was spring break for us in Toledo, and we were in Florida, and we got the news that during the testing, one of these very fine shields had ripped. And so it was really not a fun time, but they were able to recover, they were able to test and make sure that nothing like that happened during the deployment. And the deployment starting Christmas morning, 2021, until it reached the Lagrange 2 point beyond the moon, was basically flawless. It was so perfect. I mean, the nominal mission is 5 years. If Webb lived for 5 years, that would have been exactly what it needed to do. They did everything so flawlessly. We have at least 20 years of lifetime. So we're so grateful for that and very excited. So it's just remarkable. Let me give you a couple little comparison points. This is just showing you again that if you consider the fact that the Earth is about 150 million kilometers from the sun, then James Webb is about 1% of that distance from away from the Earth, and you can see how far it is relative to the moon. It's about 4 times further, right? You can see in the schematic. So compared to Hubble, which you guys are probably quite familiar with, right? Hubble was launched in 1990. Unlike James Webb, it is in a low Earth orbit. And the extraordinary thing about Hubble, which I love, that's been most of my career. I actually didn't know what I would do with James Webb for a long time. Hubble, because it's in this low Earth orbit, right? NASA was able to train astronauts to walk in space, go to the telescope, pull out instruments, give it new batteries, put in new gyros, giving it new life over and over. So that happened 4 times, and it is still operating today, despite being launched in 1990. So yeah, that has been another extraordinary story. And that has been the spacewalks that allowed it to do that. The other thing I want to point out is the little picture up in the right. So Hubble, it has a 2.4 meter diameter mirror. That's about 7 feet tall. Okay, you can see it's just a little bit taller than that person. That's the silver mirror on the left. James Webb is 6 meters across, 18 feet. So imagine, how tall is the ceiling?
About 68.
16 feet, okay, so it would go through the roof here. Imagine sending something that big into space. That's the reason they had to develop the technology to fold up the mirrors. You can see that it's in this honeycomb pattern, right? So it has the flexibility to fold up and then unfold, as we saw. The other thing that's different between Hubble and James Webb is the wavelength of light, or the energy of light that it studies. Hubble looks in the visible or optical. That's what we can see, right? And so if you looked at something like the nebula on the left, Hubble can see bits of light, but there's a lot of dust in this area of star formation. And so Hubble cannot see through that. James Webb can. So by going to the infrared, you can see through the dustiest regions in the universe. So if you want to know what's happening when stars are just being born, you need James Webb. If you want to see the coolest objects in the universe, planets, failed stars that are called brown dwarfs, you need James Webb. And if you want to see the most distant galaxies that we can imagine seeing in the universe, you need James Webb. So these are the three targets for, and the three science cases that James Webb was mostly designed around. And so just to point out on the right, we could count them up, but we won't take the time, but you could imagine counting up how many stars are revealed in the infrared image on the right compared to the Hubble image on the left, right? You can see a lot more stars. You're basically seeing right through the dust. Basically what's happening is the infrared light can come through the dust, whereas the dust blocks the optical light. I'm gonna highlight actually quite a lot. I have amazing colleagues at the University of Toledo, and they are doing some extraordinary things. We have been very fortunate, I think. Also, we've worked very hard to, and we've had great success. So in cycle one, University of Toledo was literally one of the top 5 institutions in terms of success rate with James Webb. We were also the smallest. We were the only institution in Ohio. We have the majority of all of the Webb time in Ohio. That's right down the street at the University of Toledo. And one of the things we're really proud of, we have had 3 of our graduate students, right? They're working on their PhDs. They're still in training. They have successfully led proposals on the James Webb, even with sort of the 10-to-1 oversubscription. So this is the Space Telescope Science Institute. It is the entity that runs Hubble and Webb. And I love this building because this is where I did my first postdoc. I went to Hopkins for grad school, which is right over here. And then if you cross San Martin Drive, you get to Space Telescope Science Institute. And because they run Hubble and Webb, and soon, I hope you will get to hear about Roman, which is the next NASA mission, which hopefully will fly. It's all ready to go, 2026 or 27. So we are on, we get to lead and help form ideas of how to keep improving Webb, the data products that they deliver to the community. Okay, and so let me tell you a little bit about what we do at Toledo and sort of the broad range of research. But before I do that, I do want to show you a little bit, just so we're all on the same page, the scales of the nearby universe. Okay, so this is a little video, hopefully it's gonna play. And what we're gonna do is we're gonna kind of start very quickly on a ship that's sitting right outside of Italy, and then we're gonna zoom out. And you'll see a little bar. Every time that bar goes back out, we're looking at another factor of 10 in distance away. Okay, so let us make sure my phone's on. There we go. All right, now we're leaving the boat. Here we go. Watch to the left. Okay, what do you see? You see a pretty recognizable landmass right there. And our incredibly beautiful home. Now let's keep going on this journey. Here comes the moon. Pretty soon Mars will come into view as we zoom out. There's Mars, and here's the inner solar system, our terrestrial planets. There's the asteroid belt, and now we get to our gas giants, Jupiter and Saturn, and our ice giants. And the Kuiper belt is that second ring that you can see of icy bodies. Now we can see that the sun is starting to kind of disappear and become just a point of light like the other stars, right? So if we keep backing up, we're going to get a view of the sun like we see the closest star, Proxima Centauri, and now here's our nearby solar neighbors. This is the range of distances where Professor Cushing works, brown dwarfs, nearby planets. Still very close. Now we see some star formation. Here comes Orion. This is one of the closest, most active regions of star formation. Professor McGath works on that. And we can see the spiral arms in our own Milky Way. And here is a view of our own Milky Way. We've learned a lot about its structure with satellites like Gaia. And our nearest satellite galaxies are coming into view. This is, we're still in the local group. There's about 80 or so gravitationally bound galaxies. That's our local group. And if we keep zooming out, this for me is quite close still. Now we see some other groups coming into view, and then look over there on the left, that's the Virgo cluster of galaxies. And then Laniakea is our local supercluster, and then our supercluster complex, right? So galaxy groups and clusters are clustered together. The universe likes to live near each other. And so with this scale, as you keep adding factors of 10, we very quickly get to 10 billion years, which is about the scale of the observable universe, right? So if you think about it, the universe is 13.7 billion years old. And it'll zoom right back in so we can end up where we started. The universe is 13.7 billion years. So we cannot see any, so we can see objects that are 12 and now with Webb's almost 13 billion light years away. If you are 13 billion light years away, light has a finite speed. That means we're seeing those objects as they were 13 billion years ago. Just a fraction of the age, when the universe was just a fraction of the age that it is now. So the universe is this very cool time machine. Okay, so I want to highlight a few of the research areas that we have going on at UT with Webb. This is Professor Cushing's group. This is sort of the nearest to our own solar system. It's in that area of, it's not as close as Proxima Centauri, that the nearest star, but it's in the realm of like the closest few hundred stars to our own sun. And what they do is they look at the coldest failed stars, getting almost at that planet star interface, and they study all sorts of molecules. When it gets that cold, they like to joke that the temperatures, the surface temperatures of these objects that they look at are about what the temperature we have in this room, right? So most stars would not be impressed. That's pretty cold. But at that point, you can form molecules, and so they can study with Webb the molecules that you find on these alien worlds, and they are detecting all sorts of different things like water and ammonia. In some cases, they have detected methane, and phosphine has been detected as well. Now, this is not their discovery, but I know they know the people who did find this. And I think this is one of the most promising areas for James Webb. It was designed to look at and look for organic molecules on planets around other stars, around exoplanets, as we call them. And in fact, Webb has found can you imagine? It's literally able to detect molecules in the atmosphere of a planet around another sun. And it has detected methane and carbon dioxide, which we do believe are two critical molecules for the potential of life. So that has now been discovered in planet K2-18b. This is just an artist's rendition of the planet itself looking at its parent star. And I know that there are more observations coming, and we are hearing rumors that there are other planets where they are seeing some interesting things in the atmospheres. Probably those will get released as press releases in January when we have our big meeting, one of our big annual meetings. So Professor McGath works on Orion. That's coming out and looking at a chunk of our galaxy. It's a little further away. And he looks at the birth of stars. This is a really cool little view of some of his data. And you can see all of these colors, right? Those colors are all coming from different elements that are there at the birth of stars. Basically, we know that that's material. It's basically the guts of massive stars, previous generations of massive stars that have been spewed out. They've collected, they've cooled, and now they're being incorporated into the next generation of stars that are being born right in front of us. And it's pretty turbulent. You can see these jets of material are being fired out. There's all sorts of dynamic activity going on as these stars are being born. And so one of the things we like to say, right, is that not only are we in the universe, right, the universe is in us, all of the guts of those massive stars that we see right in that cool star forming region, those are the elements that have ended up in our own solar nebula and in our body. So we are literally the guts of previous generations of massive stars. So thank you, Cynthia, for mentioning the stamp. There is the stamp of the Phantom Galaxy. So if you take a step back outside of the Milky Way, outside of the local group, one of the projects that I'm working on is with FANGS, and we are looking at 38 Milky Way-like galaxies. But what you can see is this incredibly rich, this is only half of them, but you can see this incredibly rich variations in terms of what they look like, right? They have differences in their center. Some have small point-like centers, some are more extended, some have little, well, let me see if I can just point to it. You see that second one from the top? You see that bright ring? This incredibly intense region of star formation. And these star clusters that I study, they're like kind of the key. When you have intense star formation, you always form star clusters. It's just full of these just forming star clusters in this beautifully tight ring, right? So gravity's in play and all sorts of other processes are happening. So we're having a lot of fun working on this data set, and I'm trying to finish a paper on it. This is one of our galaxies, just to give you a little closer view. It'll go back and forth between Hubble, which is visible, right? You're mainly looking at stars, and there's James Webb.
Oh, wow.
So if you keep a look out on the optical, the visible light, the dark regions there that's where the dust is, they start glowing. So the dust is blocking you in the optical, but then it's warm enough that it's emitting light that we can see in the infrared. I used to think that galaxies were most beautiful in their starlight, and now I think I might have been wrong about that. I think their dust is actually quite spectacular. They are. And so this is one of my favorite galaxies, and it is my getting at my cycle for time that's coming. The observations are scheduled for December. So I'm really looking forward to getting them. This is the Phantom Galaxy. And we'll zoom in a second. Keep your eye on this thing right here. That is the phantom void. It is the largest hole in a galaxy that we have found out of these 38. What we think has happened is that there have been probably on the order of 1,000 supernovae that have gone off over a period of time and just pushed all of the material out into this massive hole in the gas and dust of this galaxy. On the rim of that massive hole, there's star formation. A new generation of stars is being born. We don't see it super well in the opticals. That's why we need Webb. And I have observations coming. We're basically taking spectra of about a quarter of the way around of the phantom void to see how fast is that gas moving, how much of it is piled up, how does it break up into different chunks, and what's its condition. So we want to try and understand what's triggering that star formation. Okay, so let's keep talking a bit about galaxies. And I kind of said this already, but when you're talking about galaxies and the distances that we have to go to really study galaxies, you have to remember that the universe is this time machine, right? And the reason it's very simple. Light moves really fast. We all know that, right? But it has a finite speed, and that speed does not change. This is where Einstein's theory of general relativity and things comes from. Doesn't change in any framework that you have, any reference frame. In fact, if you consider how fast light moves in 1 second, it will wrap around the Earth a little over 7 times. That's how fast it goes, which is really hard to imagine. Even given that speed, right? Even given how fast light moves, the galaxies are so far away, some of them are so far away that they have been traveling to us, not just for millions of years. And frankly, millions of years is just the blink of an eye in the time scale of the universe, but for billions of years. And with James Webb, this extraordinary facility that we have, we can now see galaxies that are sort of 12, 13 billion light years away. And so when the light has been traveling to us for that much time, we are seeing, from that distance, we are seeing those galaxies as they were just 0.7 billion years or so after the Big Bang. So they're young. We don't know what they look like today, right? They got to finish their evolution, but we can see them when they were young. So the deeper you look in space, the further you're looking back in time. So it's a really great way to learn about the universe when you have the ability to look at these distant galaxies. So the way to read this slide is, on the left is today, that's the modern universe. And if you look all the way to the right, that's the Big Bang. We were talking earlier about the cosmic microwave background radiation that was emitted here. And so this is the part where we can never directly observe anything earlier than that. That's a hard limit as far as we understand right now. But what you can see is that Hubble did pretty well. It could see back to when the universe was about 1 billion years old. Certain galaxies, the brightest galaxies at that time. Webb is now pushing into this really important regime where it's just, you can see the timeline here. It depends a little bit on your assumptions, but 500 million years, maybe just 300 million years after the Big Bang, that Webb is now seeing some extraordinary objects in there. Possibly, we think it's possible that Webb might see or might be able to see the very first stars ever born in the universe. I don't think that's happened yet, although there are claims that maybe we are seeing hints of that. So we will have to wait and see. Okay, and just a quick reminder, right? So we live in what kind of galaxy? Spiral. Okay, there's 2 other kinds, basically. If you have star formation happening, but no real organized structure. You live in an irregular galaxy, and this is an example. You can see we don't have any spiral arms. It's just sort of a train wreck kind of galaxy. And so that is how you should think of irregulars. They're just train wrecks, but they have lots of stuff going on, like popcorn going off, star formation and stuff like that. And then we have really organized what we call red and dead galaxies called ellipticals. And so ellipticals finish forming stars many billions of years ago. They don't have any gas and dust anymore. They're just old, low mass stars that are just passively evolving. Nothing's really happening. And so they're very pretty, but they're these very smooth kinds of objects. So ellipticals, spirals, and irregulars are the three kinds we have. We saw this picture go by really quickly, but let me point out our own Milky Way again. The top image is a face-on view, right? And then this image here just gives you a little bit of a edge-on view. You can see all of these beautiful spiral arms. Star formation happens in those spiral arms. There's lots of gas and dust. And then down in the center, we have a very old bulge. And then around it, kind of if you think of a snow globe, right? That when you throw the snow up, you get all those little particles around. Those, we have those in our own galaxy. That looks kind of like the snow globe, right? These are globular clusters, these very old, some of the oldest objects that we can see today. Clusters of stars that form, they have about 100,000 to 1 million stars that are all gravitationally bound together. If you want to think of what they might look like, it's like a massive swarm of bees. All the stars are kind of whipping around like a swarm of bees. So those are globular clusters, and then you can see these spiral arms, and that'll come back, those two features. I want you to remember them because we'll come back to them. Okay, so let me tell you a little bit of the story as it unfolded in my lifetime. The Hubble Space Telescope took the deepest image we'd ever seen of the universe by staring at a tiny little blank patch of sky. Imagine holding a dime at arm's length, right? And that was the size of the patch of sky that was observed. There was nothing in it that we could see. It really looked completely black. And no one knew what would happen. The director at the time basically took a big gamble. He had some orbits on Hubble, actually 400 of them, that he could use at his discretion. And he had asked a bunch of people, what should I do? And people wanted him to look at this or that or their favorite objects. He said, and someone suggested to him rather cheekily, well, why don't you just look at nothing and see what happens? Mm-hmm. And he got sold on the idea, and that's basically what he did. And what ended up happening was one of the most extraordinary, I think, scientific advances in astronomy in the modern era. Out of this dark patch of sky where people thought he would see nothing, appeared galaxies, right? A little pencil beam through the universe with galaxies at all different distances strung out, including some of the most distant galaxies that we had ever seen. So with Hubble's incredible spatial resolution, its keen eye, we were able to see what those galaxies looked like. Not only could we detect them, not only could we see how far away they were by taking observations in the right way, we also could see what they looked like. And what we found was that young galaxies, these very distant galaxies, all looked like train wrecks. They were all these irregular galaxies. So all the structure that we see today in ellipticals and spirals, we did not see that in these early pictures that came out from Hubble. So our picture of early galaxy formation has been that, well, it must be big chunks of gas, right, running into each other constantly, and that, wipes out any normal structure you might get from spiral arms. Well, that was apparently not the end of the story. This was very, very surprising. After all that effort, I can't even tell you how many papers have been written on the Hubble Deep Field or the Hubble Ultra Deep Field, right? Looking at the properties of these early galaxies. Well, Webb came along, and what Webb showed, Webb has exquisite, it has even better resolution than Hubble, which is extraordinary because it's in the infrared. It's because it's such a big telescope. But Hubble actually found that there are a number of galaxies that already have their spiral structure in place. And that must have happened much earlier than we expected. That only 3 billion years after the Big Bang, there are spiral galaxies in place. And so we've had to revise our models of how spiral structure forms and how it's stable, based on that. So that's been a very unexpected and interesting discovery. We don't know exactly in our own galaxy, right, when the spiral structure stabilized. We can do it from like very old stars, but you cannot age date individual stars for a number of reasons, because they shine in the same exact way for billions upon billions of years. So if you think about our sun, anyone know how old our solar system and our sun is roughly?
4.5 billion.
4.5 billion years or so. So anyone know how long the sun's hydrogen burning lifetime is? It's an important number, but we're fine, we're safe. It's 10 billion years. So the sun is only halfway through roughly its hydrogen burning lifetime. So, but what it means is that if aliens are looking at us, and I'm not saying that they are, but if they were, they wouldn't be able to tell you how old our sun is, because it's gonna shine the way it is. It's not gonna really change whether it's 1 billion year old or 4.5 or 9 billion years, right? So we don't really have a sense of how old it is. There's no observation we could make to say how old specifically our sun is. The star clusters that I studied, that's not true. You can actually age date them. So they're these amazing cosmic clocks, and that's why we look for them. Unfortunately, in our own galaxy, we don't have very many. We have the old globular clusters, which are not in the disk, but we don't have many old what we call old open clusters in our disk. So it's a little harder to age date the disk of our Milky Way. Okay, so I told you that Hubble says train wrecks, Webb says, no, wait, there's really cool spiral structure. So what happened? Like, what's going on? Well, we think we have some clues, and it is the fact that these distant galaxies maybe just had more dust than we thought they would. We thought they were early, they're not going to have a lot of enriched heavier elements, which is necessary for creating dust. But it does seem like potentially they have more dust than we expected. And this is an example of a nearby galaxy. It's actually two galaxies that are merging together. There's this kind of messed up one and then this little one here. This is what our Hubble data looks like. And then we were very excited when we got our Webb data, and then we looked at it, we're like, wait a minute, that just looks like a normal spiral galaxy going on. So you can see that the dust, if you're depending on what wavelength you look, it might appear to be a train wreck in one set of observations, but as you go to longer wavelengths or infrared light, you can then actually start seeing that it's a spiral and there's just dust that's messing with your view and not telling you the correct structure. So we think that's kind of what might be happening, and why we had the story a bit wrong for all those years. Okay, so I'm gonna show you, I think this is currently my favorite galaxy or favorite system. This is the antennae. Anyone heard of it's a pretty famous system. It is the closest pair of merging galaxies. So there's one galaxy down here. This is its center, its bulge. And then there's a second galaxy up here, and there's its bulge. Imagine the Milky Way, right? We have a massive spiral. Imagine Andromeda, which is actually coming screaming towards us. In a couple billion years, there's a very good chance that Andromeda is going to run into the Milky Way. We're going to run into each other, and we will have something like this happen. One of the things that's happening is all of the raw fuel for star formation that we have in our spiral arms is getting stirred up and moved around. There's huge explosions of star formation happening in this system. And then there's been a big mystery in this overlap region. So the two galaxies overlap right here. Thank you. Let me see if I can, no, I don't think my printer works that way. So we have this overlap region, we have all this intense star formation happening, and this is likely our fate, right? A few billion years from now. And so it's a really interesting system for a number of reasons. Also because in the early universe, galaxies ran into each other a lot more. And so the early universe had much stronger star formation if you integrated it all up across all galaxies, because the universe was smaller, galaxies ran into each other, the gas and dust would condense, collapse, and form stars. And so you can see how dusty it is in the optical. And it's long been thought that we are missing most of the star formation happening in the system. Back to some of the earliest infrared satellites, which had much poorer resolution. They couldn't really see, but they were like, there's a whole pileup of stuff happening right here. So we must be missing most of what's going on in the optical. Well, now with Webb, we can see all the way through. So here you can see now those dark regions, basically, you can see right through them. And the neat thing is, from my perspective at least, we actually knew about most of the star formation. So there's a lot of dust. It's making things confusing, but we actually have, and we detected some never seen before, never detected before star clusters. But we already knew about the most massive one. So it was so massive that even though it was very dusty, we could still see it in the visible. So we're now putting together a paper I'm hoping to submit by Thanksgiving, laying out what we've learned about the system now with Webb. But the mystery of, what is hiding behind the dust, we basically finally solved that. And there's all sorts of other cool niche things that we're working on in this system. But it's this amazing story, right, of these two galaxies that are running into each other, and we're watching that progression. This is early in the progression of their merger. Yeah, and that's basically what I had mentioned. So one of the neat things I should say then is, with the new Webb data of the antennae, this was my Cycle 1 program, we now have a complete map of all of the star clusters in this system. Nothing is hiding anymore, right? There's no questions, we've got it all. And so now we can really tell you what's going on. We can tell you how old things are and where they're located. And we can put together sort of the star formation history of this entire system, from these young massive star clusters, which are like young globular clusters. To go along with that, right, to follow the theme of these star clusters a bit more, we see them in every galaxy. We have lots of them in our own Milky Way of different ages. This is an example of one that's about 20,000 light years. And the only thing I want you to take away is that when they're close, when they're in our galaxy, they look like this. And you can see, I don't know if you can see from back there, but there's all these little red dots. Every single one of them is a star that is part of that cluster. So there are probably close to 100,000 stars you could get all the way down in this system. Now imagine zooming out like we did before, pushing this thing far away in a more distant galaxy. All the light is going to come down into a smaller region. This is what those kinds of clusters look like in my FANGS galaxies. Right, so we have to have specialized techniques to pick these out from individual stars from background galaxies and things like that, but we can do it. We've developed a huge amount of machinery to do that. And then the big surprise with Webb in this field, or at least one of them, is that we actually were able to discover this is not my discovery, but in 2022, soon after Webb started putting out data, there was a discovery of individual star clusters for the first time. These dots, and they do look kind of like what I just showed you, right? This galaxy is only a few billion years old. It's really, really far away. You can see it looks a little bit distorted. The only reason we can see this level of detail in this very distant galaxy is because there's a whole pileup of mass from other galaxies much closer that are boosting the light. It's getting a big gravitational boost. And so we are able to, it's like a big giant magnifying glass right in front, right? So this distant galaxy is coming through this giant magnifying glass and we can see it. We can see now all of these individual globular clusters in this distant galaxy for the first time. So there's like a paper a week now coming out on this system. And it is quite lovely. It's called the Sparkler. So if you ever look, you'll see many papers and a growing number on the Sparkler. And so this is this is actually like my vacation project because I work on a nearby universe. And so one of our colloquium speakers from a few years ago, I was at a conference in Aspen and I happened to talk to her and she was holding on to a secret, which was this system, but she doesn't work on star clusters. So she was asking me about it and finally she's like, can I just show you my data set? She's like, I think there's star clusters in this, and this galaxy is even further away. So it's even younger than the one that I just showed you. And it's actually an elliptical, which means it's dead. It's already formed all its stars. It's already formed all its star clusters and nothing else is happening. So the universe was not supposed to be able to make galaxies this massive, this early, and this dead. So we're still trying to figure that piece out. But part of that is trying to understand what all of these little star clusters that are associated, that formed with this galaxy are telling us. So that's been a really fun project for me. And you can see they're a lot fainter, right? So this galaxy is not quite as highly magnified, so that hurts us a little bit. And the clusters are older, so they faded more. So this is really getting to the edge of what we can do even with James Webb. But we actually have been able to sort of put together the formation history from the clusters. And we know that it continued. We think it was sort of continuous and then boom, stopped right when the galaxy stopped. So the clusters and the star formation just ended a couple billion years after it started. We don't know why, possibly because of some interactions. Okay, I'm gonna finish up, just sort of, we looked now at the relic. That's what that galaxy was called, right? That was getting back to like maybe just a couple billion years after the universe was born. And now to really get even further back in time, right, we sort of need to move to simulations. And so one of our faculty, Eli Gisbal, and graduate student Ryan Hazlitt actually make these really sophisticated models of the first stars. They use the supercomputing facility down at Columbus to do this. So you can see all this, gas being thrown out as these stars are forming and basically exploding. Okay, so we've gone on this voyage, right? Kind of close, and we've gone pretty far out, pretty close to the Big Bang. This is about getting close to us, the edge of the observable universe. This is a simulation, but eventually, hopefully, we're going to get there. If Webb does a super, super deep field, and I think eventually it will. Right now, the resources are way too precious, I think, for any individual group to get that much time, so it's a peer review process, but I think eventually we'll get some real deep observations, and hopefully then we will actually directly detect some of the first stars to form ever in our universe. And so just to summarize a little bit, right, James Webb is really revolutionizing what we know about the key processes of how galaxies formed early, like the sparkler, and how galaxies nearby, right, and are continuing to form today, what's happening to them, and maybe even telling us a bit about the future of our own Milky Way and Andromeda. Guaranteed there's going to be surprises to come. Keep your eyes on the news. But I want to end by bringing us back to Earth, right? In 1990, the Voyager 1 probe was on its way out of our solar system. When it was about 4 billion miles from Earth, it turned around and it took a picture of Earth. Can you guys see where Earth is?
In that stream?
Which one? There's a few different streams coming down.
A little bump in the green one in the middle. Is there? Down toward the bottom. Oh.
Well, let me show you where the Earth is.
Oh my gosh.
4 billion miles away. This is what the Earth looked like to Voyager 1. And I think it's very appropriate, right, to remember what Carl Sagan said about this picture of the pale blue dot, which is our world, right? And I think this is what connects astronomy and S.A.V.E. and our planet. And I'll read a little bit of it to you. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you have ever heard of, every human being who ever was, lived out their lives. So that is, I think, it's incumbent on all of us to remember that our Earth is this very small stage in this really vast cosmic arena, as we've just seen today. It is the only world we know that harbors life. There are no aliens, right? One Atlas, 1A Atlas is not an alien vessel. We have gone to Mars. We're sending things to the icy moons of Jupiter. Maybe we'll find evidence of microbial life someday, but we have not yet, right? The only life we know is here on Earth. And so for better or worse, right, Earth is where we make our stand. It's been said that astronomy is a humbling and character building experience. And I think there's no better demonstration of the folly of human conceits than that tiny little dot viewed from 4 billion miles away. And so Carl Sagan's final words on that were, to me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Wow.
So thank you. I will take any questions.
Has there been any cutbacks in your funding? It seems very worthwhile, but some of the great programs seem to be getting cut.
Yes, yes, we are struggling with funding. Some of my colleagues have had long delays and some have had accepted programs that have then been rescinded. So yes, it is hitting us hard.
I had heard 25% for NASA.
Yeah, there's a lot of confusion. And I think with the government shutdown, we have less information at the moment. So I can tell you for James Webb Cycle 4, I have that data coming. And we've been told We don't have a budget yet. We don't know how much money we will be able to send out. And so cycle 4 observations have been going on for several months. And so I know people are, waiting so they can pay their grad students and postdocs and stuff. So we will see. Yeah.
Yes, the Webb orbit, is that in a oval orbit or round orbit or no orbit?
Which one?
The
The James Webb?
The Webb.
I think it is fairly circular. If you think about the way the Earth orbits the sun, we have a slight eccentricity or ellipticity to our orbit, but it's not much. Mars is a bit more eccentric than we are. It's really some of the outer planets, Neptune and Pluto, that get very elliptical. But most things are fairly circular in the inner solar system.
Is there any damage that has been done to the Webb so far?
I know there was they paused it because there was some issue with a micrometeor, but so far it's been fine. There's been no damage. It's worked beautifully. Hubble kind of in the last decade has had has had to go into safe mode periodically, and they have to sort out what's wrong. They've been able to bring Hubble back every time, but nothing like that has happened yet with Webb.
I'm trying to figure this out in my mind without looking stupid. So it's rotating, or it's revolving around the sun.
You're talking about James Webb?
Yes.
Yes.
Okay, it's not just shooting straight up.
No, okay.
I
So
was really confused about how if it just kept going and going and going.
no, it's tied to right there. We have the sun, Earth, Moon system, right? And so it's actually tied to the Earth Moon system as it orbits around the sun.
So it's getting a view of everything that's
It will-
around.
It will get a view of all parts of the sky at some point during its orbit.
Does it ever go like this as opposed to
No,
this?
It
Okay.
stays in the plane
Oh,
because the
okay.
Earth and the Moon stay in the plane. So yeah,
Okay.
it's tied to the orbital plane that all the terrestrial planets are in.
Thank you. How is Webb doing with black holes? Being that, am I correct in saying that probably at the center of most galaxies, you're going to find a black hole?
Yes, so an interesting story. When I was at Hopkins, I was a young grad student, and my office mate, she was a couple of years older than I am. And so our advisor was the principal investigator for one of the cameras that went on Hubble. So he had a bunch of data that came with that effort that he put in. And so the project that he had, which was the only project going at the time, was to look for evidence of supermassive black holes at the centers of galaxies. So she actually gets credit for really nailing down for the first time outside of our own Milky Way, the first supermassive black hole in a galaxy, and then the second. And since then, right, the question has become not do supermassive black holes exist, but do supermassive black holes exist in every single galaxy? And the answer seems to be yes. So yeah, Webb does a great job, especially when you're looking at the centers of really dusty galaxies. One way that we know black holes grow is through that process of galaxies slamming together. Basically, the galaxies slam together, their nuclei eventually merge, and the supermassive black holes in each one individually merge together, right? They come together. But in that process, there's a lot of dust in the way. And so James Webb allows you to see through some of that. And so, yes, I think there has been a big discovery space in the AGN or supermassive black hole too.
What about the presence of dark matter?
Neither one of the Hubble nor Webb can really do much.
I was just reading something about, the light travels 186,000 miles per second, but it might not be that much because the dark matter is slowing it down. So I just wondered, if that entered into anything that you.
I don't know of any concrete detections of that. The way we generally, you guys have all heard of dark matter? Okay, so there's a few different ways that there's a few different reasons why we believe dark matter must exist. One of those is if you look at our own galaxy and all other spiral galaxies. If you think about, if we calculate what we can see from the light and we convert that to mass, they really shouldn't be holding together. So there is additional mass, and we call it dark because it's not emitting light that we can detect. That is sort of like a glue, right? It's a gravitational glue that's holding our galaxy together. And then in clusters of galaxies, like the Virgo cluster that we saw, there's a lot of this gravitational glue. It's way more than the mass of all the galaxies put together. It's like 10 times more than. So we have these different ways where we know there must be something. It's not emitting light, but it's got gravitational, it's a glue, right? It's gravity. And so the thinking right now is it's some kind of particle, a neutrino that interacts weakly and all sorts of things. So it's right now particle physics is hopefully dealing with it. But we have not made a lot of progress in figuring it out for the last half century or so.
Even the people working with it haven't figured it out.
No, I haven't figured it out.
Is the hole that you described and the one that you showed us
Mhm.
is not a black hole?
No, that's a great question. No, it's not a black hole. It's just, and so I'll explain a little bit why we know that, but it's literally just, there's nothing there. The gas and the dust has just been pushed out and it no longer exists, even though it's usually diffusely all throughout galaxies. So it's this big void or hole or bubble that's been blown because of these supernovae pushing out all of the gas and the dust. Now, the reason it's not one way to think about black holes, I know they have this really monstrous reputation. They're actually really windy in this sense. They might be really massive, but their sphere of influence is tiny. When you think of how big space is, the probability of running into a random black hole is like impossible. It's such a small sphere of influence. So, to put a little bit of proportion on it, maybe something you can get your arms around. In our Milky Way, the supermassive black hole is something like a few times 10 to the 6, a few million solar masses. Its gravitational influence, though, is mostly like on the order of the size of our solar system. Right, and we know like that most of the stars are well beyond that. So it's kind of really like the most intense gravitational influence, and you don't want to be in there for sure, but it's really, really pretty small. So it could not do anything on the large scale that we were looking at for the phantom.
I'm going to risk my life because a lot of people who know me will think I'm crazy. Well, I want to challenge you, but I'm not smart enough to challenge you.
Please challenge me.
I have a friend who is a former Catholic priest who was an exorcist.
Mhm,
In talking to him about the existence of Satan or the devil,
mhm.
he says the mind of man is able to project beings like that, and every being that he had exorcised was the fact that the mind of man was able to project that and then judge it and experience it in the world. That's my analogy to what I think you're at regards to, you know enough about the universe that you know that there's no evidence of other life besides on planet.
Mhm.
Okay, so that's part of it. Now, I'm trying to make this simple enough to say, what's your take on this? Because I know there are people like Hal Puthoff
Mhm.
and other people who are scientists, physicists, who go beyond what you're saying. In fact, they would say, yeah, there is not only the possibility, but that there's things like remote viewing and communication telepathically. And that deals with consciousness,
Uh-huh.
which if you're right, it has to do with, just like creating a demon or the devil, you're saying that everybody that is not in science where you are is wrong. They're making it up, like quantum physicists, and I do know a few of them, but not personally. You probably do know some who would say, yeah, we do have evidence of alien life and non-human intelligence, including let's say, the Disclosure Project, and which they're trying to come up with the evidence of non-human intelligence. Are you seeing where I'm coming
I
from?
think I see parts of, let me address what I can, and then we can keep discussing.
Okay, go ahead.
Okay. So my statement that about, no evidence for life, let me make it clear, that is no current evidence for life off this planet. Do I think that there is likely to be some kind of life elsewhere? Probably. We are discovering thousands and thousands of planets. We're discovering, more and more Earth-like planets, even though they're really hard still for us to detect. And we're finding them in the habitable zone, and so good. I think on balance, yeah, there's a pretty darn good probability that there is life off of this planet. Do we have evidence for it directly? No, we don't. That's the difference.
Okay, somebody like Danny Sheehan,
Uh-huh.
who's got his PhD, not only in theology and philosophy, but became an attorney who's a fairly good constitutional attorney.
Uh-huh.
He's the one that's leading to get the information from the government about extraterrestrials.
Okay, so sorry, so you're worried about whether the government is hiding stuff?
No, about the reality, because it seems whether it's like Donald Hoffman, I think that's his name, or Campbell, who's in the game theory, and then he's a physicist who actually works with the government to help project what countries would do in order to win a war.
Uh-huh.
Game theory. And he believes that there may be, but he also believes that something doesn't exist unless you perceive it and then judge it. I mean, there are physicists who are at that level. Do you know some of them that are at that level that would be challenging even your position about non-existence of information about it?
Well,
Do you
okay,
see what I'm saying now?
I think so, but I think we're talking past each other a little bit,
Mhm.
because consciousness is a whole separate kind of discussion, right? We have to talk about that separately, and we have to take that out of what kind of concrete evidence I'm talking.
But if I took out light and matter
Uh-huh.
in space out of your thing, what do you have left? Because that's basically the world that
And
you're.
gravity, and I have many things left
Okay,
besides.
frequency and energy is still existent, even though it may not be matter. But do you give some credit that there are maybe some people who are that smart, who do know are intelligent, that there is an intelligent life that maybe on the level of consciousness or at spirit, if you want to include it, that you're not on that level, so they may
Okay,
exist?
Let me say that.
Okay, go ahead.
I have met on the order of 10 Nobel Prize winners in physics.
Okay.
So I do have an idea of the extreme end of human intelligence. And even at the extreme end of human intelligence, right? We see people go off the deep end, right? And so it's not that they're going off the deep end. I think we're talking about two different things. I'm not challenging anything about consciousness. I'm not saying anything about, right? So I am talking about the kinds of evidence, physical evidence that we can gather in front of us. And I'm saying nothing about the rest of it, right? Imagine what would happen if aliens came to our planet and they were Buddhists. How would that freak out all of our religious society and things like that, right? That would be a pretty mind-bending, pretty fun experiment. So there are many things we can imagine. And I am good. And so you are talking about many, many different things, and I am narrowing the problem down to just what I know and can see and have evidence for and can reason about. I will not discount any of the things that they are saying. And they may be right. I don't believe the government is hiding anything. I know plenty of my friends have worked at NASA. I worked at NASA for a year. It's not, I don't think the government is hiding anything. I mean, they did hide when they discovered gamma rays, but that was for a defense purpose, and that was in the 60s. But consciousness is not, that's not where I can give any feedback, and I have different thoughts on it, but they're apart from this.
So,
90 minutes.
Yeah.
okay, so the last thing, so there probably does not exist in the Vatican, ET or alien files that say, Diana Pasulka visited and actually went through and found evidence that they had of ET, an intelligent contact that goes way back before even the Bible was. So you're saying that you can disallow that and they're making that up and that's false information?
No.
I can say
Okay.
that my, that's an opinion. I can say that my opinion of something like that is, and I can also say I'm ignorant because I've never studied it, so I
Oh.
have no idea, right?
Mhm.
I don't wanna speak on things I know nothing about. So,
Okay.
but I tend not, right, so there may be people who've studied it and they firmly believe that, but to me, that is an opinion. If someone is supposedly hiding something, then you need to have, I mean, you know, so at that point, it's not it's out of the realm of science for me. That's an opinion.
Okay, so it's more like the priests who became aware of the fact that, yeah, there could be experiences of demons and devils, but they don't really exist because it's a projection of the mind. That would be one example of it not being real. Is that correct? That's kind of a little bit,
Again, like, I cannot offer any opinions on that,
Okay.
right? So,
but
We have another, person up there with the hand raised.
Just a short question. Does the science community in general consensus, believe that space and time had no beginning and no end?
no, I mean,
You speak of the Big Bang, I
Yeah.
know, but.
the prevailing theory, and I will say that, almost every astrophysicist that I am aware of believes that the universe did start in a big bang.
Okay.
And, you know, and so what we're arguing about, what we have been arguing about for a while had been, how would the universe end? And the way we think it will end has changed radically, honestly, since 1995, when dark energy, not dark matter, but dark energy was discovered.
Mhm.
Right, and dark energy is this, we're still getting our arms around it, it's still pretty mysterious to us too, but it seems more and more very orthogonal and different observational works that really strongly support the existence of dark energy. And what it is that the universe seems to be accelerating in its expansion rather than slowing down. You can imagine if you had a big explosion, the Big Bang, right? Everything goes up. And from there, the universe should be slowing down in the rate at which it's growing, right? It's decelerating. But that was the model I grew up with. That's what I learned in undergrad. That was probably the likely one. But in 1995, and they won the Nobel Prize for it in 2012, I believe. And in fact, one of the guys was in Space Telescope. We used to be like two of the only people in the building at 9 p.m. at night. He was there doing his work. I was there doing my work, but I just had a kid, so I had to go in and make up time because I couldn't be there during the day all the time. But yeah, so Sir Adam Rees was one of the people who discovered dark energy. And so we think the flavor of what the universe is how it's going to end has changed in our understanding, but not the beginning. Nothing has changed that.
Thank you.
I'll let you know if it does though.
We certainly have expanded our consciousness. This is a wonderful presentation again. I guess I personally would just like to thank you for putting in that wonderful quote from Carl Sagan on that sense of how everything is out there, but it's also here. It's here. And to keep that tension alive in our lives. What's good, as someone had said earlier, I think Sylvia, you have said to me, well, it's good to be here, but we're talking about something much bigger than the problems we face every single day. So it was really a wonderful presentation. We thank you.
Thank you.
And S.A.V.E. has a little tradition that they give a handmade pen made of local wood to our guest speakers. So thank you so very, very much. Yes.
Should I open it?
Oh, if you'd like to, yes. It's really pretty, very beautiful.
The paper is beautiful.
Well, she's opening that too. Our next lecture is January 20th, and it's on hydrogen, the role of hydrogen as for use as a sustainable future idea or thing. So join us on January 20th, and be alert, it'll be here unless the weather is terrible. And then we'll put a thing, I don't know how we can tell everybody, but, you know, it's scheduled for that day and our members know they will get the information. And I'll get, and we can put it on like, lifelong learning, you know, and other things. So I hope it kind of gets, you know, transmitted to everybody, but I don't know how to do that.
And
So-
as you leave this evening, just to take some of the ideas from this evening home with you. We just have some little sticky notes. You can take one, it just poses a question for you to think about.
Or you can use your phone, take a shot of it, and they got
I
all kinds
did.
of questions and take.